to the change in position. All right. Speed, we'll dive into this more in due time. Right now, just kind of understand this definition. The speed is the absolute value of your velocity. So it's strictly how fast we're going. So if we go back up here to these 96s, the speed is simply how fast you're going. We don't care about the sign. So velocity is a little more descriptive. It gives you your direction. Speed is strictly how fast are we going. Doesn't matter the direction is increasing or decreasing. All right, speed gets a little more complicated with that than that, but for right now, that's good enough. Next page, acceleration. So acceleration is the rate at which your velocity is changing. So let me rewrite that just a bit, not in the big fat yellow though. It's gonna let me. So I'm gonna write it as this. It is the rate of change, I think a lot of you know this already, of velocity. It's largely what that first sentence is saying anyway, but I want to write it like that just so we can see this little phrase. So the acceleration measures the rate of change of your velocity, and what we've now did today, what we've been doing here for the last week or so, we would hopefully understand the rate of change is what our derivative is. So when you see the rate of change of your velocity, that's nothing more than saying the derivative of velocity. These two mean the exact same thing. So a lot of times when we're in person, people, 2 days ago when we do a second derivative, people will like raise their hand, why would we ever need to take a second derivative? Here's one of the main reasons we would want a second derivative. Because if we understand now, if I give you a position equation like we did on the front page, the first derivative is your velocity. The derivative of your velocity is your acceleration. But wouldn't the acceleration now have been the second derivative of your position? All right. So that's what all these little things are saying. So we can write this as your acceleration at any time. You could also think of it as the change in velocity over change in time. So it's the derivative of your velocity. Or it's the second derivative of your position equation. So it's either the first derivative of velocity or the second derivative of your position. All right. A few more things to keep straight. If I have a positive acceleration, and again, keep in mind, this is the rate of change of our velocity. So if I have a positive acceleration, that would tell you that your velocity is increasing. If you have a negative acceleration, and the acceleration is the rate of change of your velocity, like we set up here, then a negative acceleration would tell us that our velocity is decreasing. Okay? A lot of stuff to keep straight here. Okay? Especially with the quiz coming up shortly, a lot of stuff that you want to process and keep straight. All right, so number 2. What was the acceleration of the rock in the example above? And by that I mean on the previous page. So let's write the original equation from the previous page. It was h of t equaled 160t minus 16t squared. So we'll tie a few things together here. If I take the first derivative of this, which is easy in and of itself, we could use this notation. We also could have said that this is v of t. The first derivative is your velocity. So either one of those notations would be fine. But that's our velocity. We want the acceleration. The acceleration, we said, is either the second derivative of your position. So let's do that. So we get a negative 32. It would also be the first derivative of your velocity. Or you could just say that it's a of t. All three of those little things could be set equal to a negative 32. So we just kind of understand this little flow. Our acceleration is either the derivative of velocity or the second derivative of your position. Either way, we get a negative 32. Those units would be feet per second squared, because we're now doing velocity over time, so that's feet per second divided by seconds. So in terms of the first thing, what was our acceleration of the rock above? We're going to get this. I then want you to tell me what was the acceleration at 2 seconds. So if we then say, you can't see my screen? Interesting. Now can you see it? This is usually what happens in 7th period all the time. See if this is going to work here. All right, it says it's sharing again. Are we seeing that? We see it now? Yeah. I'm getting, yeah, okay. All right, so I don't know where I lost you. But what we just found was our acceleration is the derivative of velocity, or the second derivative position. It's a negative 32. The next question then is, what was the acceleration after 2 seconds? So what we would just want to do is evaluate the second derivative at 2. But since our second derivative is a constant, you're still going to get a negative 32 feet per second squared. So that should go at the bottom as our acceleration at the time of 2. Okay, is that better? It was good I was muted. Hopefully you don't lip read there about 10 seconds ago. So we can see and you can hear me now. We're good? I was wondering, I kept asking, can you see the screen now? And nobody was really saying anything because you couldn't hear me. All right, that explains a lot. All right, so here we go. So here's where we kind of left off. Second derivative was a negative 32. I then wanted you to evaluate it at 2 seconds. It's a constant, so it's always a negative 32 feet per second squared. And then we get to this question. This question is, why is your acceleration negative? So again, this, if you've had physics before, hopefully it's somewhat familiar to you. Why is our for this model, a block or a rock gets blown up into the air, falls back to Earth. Why would we always have this negative acceleration? What's causing that? Eva? Yeah. Good. That's gravity, unless it has a rocket or a motor or something that's impacting its speed. If it just goes up on its own, falls back to Earth on its own, it's gravity. You are probably more familiar, what is it, 9.8 meters per second squared? That's probably what you're more familiar with when we start talking physics units. But if you convert this into feet per second squared, it's a negative 32. All right. So gravity is always making our velocity decrease at that rate, negative 32 feet per second squared. Okay. Okay, where are we at? Let's see. 53. Yeah, we'll get into this here. We'll at least set this up. So the last little rules here, and then we'll get into a bunch of problems here as you look through the rest of this paper. Other rules to know about velocity and acceleration. I'm going to actually go back to here and explain these because I think it'll make sense. That's why I like starting with this problem, because it'll tie those last couple of definitions together pretty well here. So let's go back to this problem. If I ask you in this model what's going on at 2 seconds in terms of our speed. So at the time of 2, if you throw something up into the air, in this case it's a rock that gets blown into the air, in terms of its speed, would we be speeding up or slowing down when that rock goes up into the air? What would we think would be happening? Does our speed increase or does our speed decrease? It's slowing down. Okay, so at the time of 2, our speed would be decreasing. We would be slowing down. If you throw something up into the air, you hit a baseball into the air, you throw a football into the air, it takes off quick, but eventually it starts to slow down the further and further up that it goes. At that time, so now go up to your graph. So hopefully it's not too messy. I'm going to try to clean mine up just a little bit. At this time, we knew that our velocity at 2, we had found that over here, was 96. The most important thing here, though, is just identify that our velocity is positive at that time. And I'm not making that up. We've already done it. Here was our velocity at 2 seconds here. On the next page, what did we say our acceleration was not only at 2 seconds, but all the time? Okay, did we all agree that the acceleration was negative the whole time because of gravity? All right. So notice how at this time of 2, your velocity and acceleration have opposite signs. That combination of values for our velocity and acceleration, that is why we're slowing down. We are moving in a positive direction. That's what a positive velocity means. Our position is increasing, but our acceleration is pulling us in the opposite direction. That is why we slow down. If you throw your pencil in the air right now, you throw a ball into the air, it's moving in a positive direction, but you have something acting on it, pulling it back down. If we go over here to 8, so if I ask you what was our velocity at 8, we already know this, even though it's really messy. I have it right here. We would have said that that was a negative 96. Oh, and before we even get to this, once we hit this highest point and we start to fall back to earth, so the rock is coming back down, the ball that you hit into the air is coming back down, what do we know is going to happen to our speed of the rock as we fall back to earth? Are we going to be slowing down still, or are we going to be speeding up? Speeding up. The reason we are speeding up is because of this. Our velocity at 8 is a negative. We've already identified that here. And then on the next page, we said our acceleration is always negative. So not only do we have our acceleration pulling us in this negative direction, now that we're actually going in that direction, that is the reason that we start to speed up. All right, we follow that? So if we go back to what these are defining in bold here, those are the first two. So if we look at this one and we look at this one, if your velocity and acceleration have the same signs, like that rock falling back to earth, we're going to be speeding up. If our velocity and acceleration have opposite signs, like when the rock is going into the air, then we're going to be slowing down. All right, and we all know that already. We're just formalizing a little bit with words like velocity and acceleration. Number 3, let's go back to our graph. 3, at this time right here, if I ask you what your velocity was, we've already talked about it a little bit. We use the derivative notation, but now we know the first derivative is your velocity. So let's get rid of that. So my velocity is 0. And then notice how our acceleration would still have to be negative here. It's always negative. What do we know is happening at this point right here? For the physics people, what's this little phrase? What's happening at that time? Anybody know this? Type it in, say it.
What time did you specify?
Right here. The time of 5. We do what? Ebba, go ahead. See your hand up there.
The object is changing direction?
Good. The little phrase, changing direction, you will hear a lot. That will happen when our velocity is 0, but our acceleration is not. So we'll kind of stop class here. That will be your third thing here. When our velocity is 0 and the acceleration is not a 0, that's going to tell us when we are changing directions. So if we don't have a graph to look at, these things here would allow us to figure out when were we speeding up, when were we slowing down, when were we changing directions. All right. I knew we weren't going to finish. This is a long one. So bring this tomorrow. Then we're going to do these problems that now reflect those items that we just got done going over and reviewing. I think we'll stop. Or are we at 53? We'll still stop. Yeah, that's fine. Because that's about as far as fifth period is going to get. I was thinking we were getting out at 49, but it was 53. But I'll cut you a little slack. We should be able to get all of this done tomorrow in this period. All right. So tomorrow, bring this. We'll now go over all these little problems that are hopefully tying all these things together. And then the thing that really kind of causes some problems, especially for those people who are not in physics or haven't taken it yet, is the graphs. That's something you want to be very, very careful of. But we'll do all that tomorrow. Hopefully we'll have enough time to be able to finish all of it in here. Okay? All right. So with that, I'll give you an extra 4 minutes to go do whatever you're going to go do, eat lunch, walk around, whatever, before you go to fifth or sixth period. All right? you have any questions on that, need any clarification, you have a few minutes, or anything else you may have a question on. If not, go ahead and we'll see you tomorrow, okay? All right, stick around if you have a question. All right, see you guys. Yeah, go ahead, Eva.
What units are the next examples then?
I didn't give you units for these. All I want you to kind of understand with these is your velocity is nothing more than your first derivative. We should have done these because these take like 2 minutes, and the acceleration is nothing more than your second derivative. So I didn't really get into units with these first couple.
I have a question.
Yeah, go ahead, Emma.
When would you know to use the instantaneous velocity?
It's pretty much always instantaneous velocity unless you can't do it, or unless it's specifically asked for an average velocity. So if it's ever asking you what's your velocity at a particular, also the way the question is written, so if it says what is your velocity at a particular time, then you would ideally be doing the instantaneous velocity. The only time you couldn't is, I think I may have one coming up. Get my mouse over there. So like right here, some keywords. So this is a little bit of what we'll talk about tomorrow. When it says average speed, then you're going to be doing the average rate of change. It kind of spells it out for you. If it uses the word approximate speed, that's also the average rate of change. Like all those little things that we quizzed on, you just want to pick up on those keywords. If it said, over an interval of time, that's going to imply an average velocity. But if it's ever at a particular time, so this one we'll spend a little bit of time on tomorrow. This is asking at 4 minutes, which would imply your instantaneous. That would imply instantaneous. So if at all possible, that's what you would like. But you could only really do that if you had a position equation to take the derivative of. And since all I gave you was a bunch of data up here, that's why we're going to have to approximate it with the average rate of change.
Okay.
Okay?
Thank you.
Yeah, no problem. How about you just hanging on, or do you have another question?